them up. Problem number 1, it says a bag contains 6 red, 4 blue, and 8 green marbles. We want to know how many marbles of each color should be added so that the total is now 27, but the probabilities will still remain unchanged. Okay, so we have currently 18 marbles in the bag. We want to add a certain amount of each color to the bag so that we have now 27. So we're going from 18 to 27. That means that we should have 9 marbles that we're adding to the bag. But we need to know how much of the marbles of each color does it need to be added to in order for our probabilities to still remain intact, to not change from the original bag to the new. So in order to do that, you're going to be using predictions. You're going to be using your prediction probabilities. So the first thing that we're going to do is we're going to set up the probability for red. So the probability of red. Currently, the probability of red is 6 out of 18. 6 out of 18. What we want to have happen, though, is we want to know, okay, how many need to be there out of 27? So we need to know how many red out of 27 need to be in the bag. So we're setting it up like this to do a cross product, a prediction. So we're going to multiply 18 times x, and that's going to give us 18x. We're going to multiply 6 times 27, and that's going to give us 162. And then we can go ahead and divide both sides by 18. Okay, in doing so, that's going to give us x equaling 9. Now, is that our answer? No, because the question asked us how much should be added into it. How much needs to be added? So if we started with 6 red, and we're now going to 9 red, how much did we have to add into the bag? 3. So that means we are going to increase by 3 red. This would be our answer, or part of our answer. Not just how many new reds are there going to be, but how much did we increase the bag by? Okay, and then you would do the same thing for the blue and the same thing for the green. So the probability of blue occurring, the probability that we're going to choose a blue marble out of the original bag, there are 4 blue out of the 18 original. We want to know how many blue in the new bag of 27. So again, cross product, we're going to do 18 times x to get us 18x. We're going to do 4 times 27, that comes out to 108. And then we just divide both sides by 18. Okay, in doing so, we find out that the new value of blue is going to be 6. So we're going to have 6 blue marbles. How much does that mean it increased by? We went from 4 to 6, it increased by what? 2. It's an increase by 2 blue. An increase by 2 blue. Okay, and then the last one, the probability for green. The probability for green is going to be 8 green out of 18 marbles in the bag. We want to know how much out of the 27. So we're going to do 18 times x. And then we're going to do 8 times 27. 8 times 27 comes out to 216. And then we'll divide by 18 on both sides. And then that finds out that we'll have 12, so x is going to be equal to 12 for our green marbles. So we went from 8 to 12. That means we increased by 4. So we had an increase by 4 green. And that makes sense. 3 plus 2 plus 4 is 9 marbles. So our bag increased by 9 total marbles to get to 27. Okay? Number 2, there are 20 red Skittles that are mixed in a bag with an unknown amount of green Skittles. If 15 Skittles are removed, and 5 of those that were removed happen to be red, then how many green Skittles can we assume were originally in the bag? Okay, so again, we have a probability that we can set up based off of the 15 that were removed. So based off of the 15 that were removed, we have 5 of them that were red, which means how many were green? 10, right? There's 5 that were red. That means that there's 10 that were green. This is based off of the 15 that were removed from the bag. Now, when we're talking about the original bag, prior to removing anything, we know that there happened to be 20 red Skittles that were in the bag. What we don't know was how many green Skittles there were in the bag. So we're just setting up a proportion to solve. Information that we know about the probabilities and information we are trying to find. So we know out of 15 removed Skittles, 5 are red. That means 10 had to be green. We know originally in the bag there were 20 red Skittles and an X amount or unknown amount of green Skittles. So if this probability is solid enough, if it stays the same throughout, then we can make an assumption about the number of green by doing our cross product and solving. So we would multiply 5 times x, that's going to give us 5x. We would multiply 10 times the 20, that's going to give us 200. And then we're going to divide both sides by 5. And so we can safely assume that there's about 40 green Skittles in the bag. Now again, that's just an assumption. It doesn't mean that that's the exact amount. It's just an approximation based off of the probability from the amount that we removed. All right, number 3, what is the probability of a vowel being chosen from the phrase Axio homework, if anybody's a fan of Harry Potter? So a vowel, who can remind us what are vowels? What letters are vowels? Veronica? A, E, I, O, U. Okay, A, E, I, O, U. Those are our vowels. So we want to know how many vowels are present in this entire phrase. So we've got an A, we've got an I, we've got an O, we've got another O, an E, and another O. So how many vowels is that? 6. Right? The number of vowels that we happen to have are 6. Out of how many total letters are in the phrase? Out of 13. So 6 over 13. Okay, 6 over 13. Now, that cannot be simplified, but you can go ahead and convert that into a decimal, which is approximately 0.46, which is approximately 46%. Okay, remember, you need to know all 3 ways of writing your probability because you don't know which format they're going to test you on. Okay, and then number 4, if there are 50 marbles of black and white, this is a question that was from like your quiz on Friday that a lot of people came up to me and asked about. So 50 marbles of black and white, what's a reasonable number of black if the probability of black is supposed to be close to 1? Close to 1. Okay, so if it's close to 1, we can safely assume that we're looking for a probability that is greater than or equal to 75%. Right? If it's less than 75%, let's say 74%. 74% is closer to the half than it is to 1 whole. So 75% or more is closer to the 1 whole range or the 100% range. Anything below that is not as close to 1 as it is to something else. So remember, we have our probability line is broken up into parts. You have 3 segments, a starting segment, which is 0, a middle segment, which is 1/2 or 50%, and an ending segment, which is 1 whole or 100%. And then you've got percentages in between that represents likely and unlikely. So when you're wanting to get close to a value, you need to figure out where is that cutoff going to be. If it needs to be close to 0, then you'd be looking at 25% or lower. If it needs to be close to a half, you'd be looking at values that are, and if it says it's really close to a half, you're going to be looking at values that are, again, closely ranged around that 50%. So for here, if we're talking about a reasonable number that could be close to 1, we're looking for values out of 50 that are going to come out to about 75% or higher. So that's looking at anything from 38 to 49. Why not 50? Why can't I put 50 as an answer, Veronica? Exactly. 50 would be exactly 1 whole. They didn't say that it's exactly 1 whole. It's close to 1 whole. So that means you can't choose 50. But anywhere between 38 to 49 is going to be a good approximation for close to 1 whole. Okay? Any questions? All right, let's go ahead and go on to the next page. We're going to be talking about tree diagrams and compound events today. Tree diagrams and compound events. So compound events, I've mentioned it before, but a compound event is a combination of at least 2 simple events in probability. Things like tossing a coin and flipping, and rolling a die, or pulling a marble out of a bag and spinning a spinner. These are simple events that you are combining together and looking for outcomes from each. Okay, we've already utilized our concept of fundamental counting principle to identify total amounts of outcomes for compound events. Now we're going to use tree diagrams to map out the entire sample space for these compound events. Now, some of these compound events are independent, meaning that what you land on for one activity has no effect on what happens to a second activity. Some of them are dependent, meaning that what you choose to happen for your first outcome will ultimately affect how you choose your second outcome. For example, if I were to ask you guys to stand in line outside in the hallway, and I say, okay, Elijah, you're going to go first. Can I pick Elijah to go second and third and fourth and fifth? No. Once I've chosen Elijah, Elijah has been removed from the mix. So right now there's 30 of you. So the probability of me choosing you to be first is 1 out of 30. But once I choose somebody to be first, your probability has now changed when I want to choose a second person. To choose a second person, your probability is now 1 out of 29. And then it becomes 1 out of 28 and 1 out of 27. Each time I choose a student, the probability changes. Those are called dependent events. Okay, so what I choose for my first outcome or what my first outcome happens to land on ultimately has an effect on the second outcome. Now, if I flip a coin, is that going to affect how I roll a die? No. Okay. If I spin a spinner and choose a marble, are they going to affect each other? No. If I spin a spinner and then spin the exact same spinner again, is that going to have an effect on itself? No. Okay. Just because I spin a spinner and land on a 3 doesn't mean I can no longer land on 3 again, does it? I could spin it and it could still land on 3 again. Okay, that's just how it works. I mean, how many times have you guys played a board game? You roll the die, lands on a 6, and then you roll it again, lands on 6 again. It's still available. It has not been removed from you being able to use that again. Okay, when something is removed and you are no longer allowed to use that, that creates dependence. Okay, all right, so tree diagrams. Again, like I said, we are mapping out a sample space based off of possible outcomes from each of the events. So for here, lunch. For lunch, you have a choice of milk or water. You can choose a sandwich, pasta, or nuggets for your entree. And you have a choice of veggies, fruit, or chips for your side. You're going to create a tree diagram that represents the total sample space for this situation. So don't write all of it out. Okay, shorthand it a little bit. You don't have to sit here and write milk and write water and write down sandwich. Use the first letter. Be lazy. It's perfectly fine. But when you're setting this up, how you're setting it up is you're identifying the different activities that are occurring. The first activity, our first activity is to choose a drink. That's our first activity here, choosing a drink, which is milk or water. So we happen to have 2 possible outcomes for our first activity. So I'm going to go ahead and just write M, and yes, I'm going to be using that whole space, and W. M stands for milk, W stands for water. Okay, then I have my second activity. My second activity is the choice of an entree. So I could choose a sandwich, pasta, or nuggets for the entree. So a tree diagram is exactly as it sounds. It's building a tree. You start off, your first activity is the big trunk. Your second activity starts building branches. If you have a third activity, it starts building smaller branches or twigs, and so on and so forth. We try to not have any more than 3 activities for your example, but obviously you can have as many as the problem presents, okay? So for here, because I have 3 choices, that means that when I choose milk, I have 3 options of entree, right? I can go with a milk and a sandwich. I could go with milk and pasta. I could go with milk and nuggets. But the same thing for water. With water, I could choose a sandwich. With water, I could choose pasta. And with water, I could choose nuggets. Now, I do have a third activity. And in my third activity, I can choose a veggie, a fruit, or chips. So that means from each of these choices that I have here in my second activity, they all have 3 little choices that are going to come out from it. So I could have gone with milk and a sandwich and veggies, or milk, sandwich, and fruit, or milk, sandwich, and chips. And I can do that with each and every one of these. That I could have veggie, fruit, and chips. And then of course we have to come down here and do the same exact thing for our water choice. Water, sandwich, and veggies. Water, sandwich, and fruit. water, sandwich, and chips. Then we do the same thing for pasta. We could do veggies, fruit, or chips. And then lastly, we do it for the nuggets. Veggie, fruits, chips. So this is a tree diagram. Now, with tree diagrams, you always want to have a sample space written out. And before we even write the sample space out, let's go back and use our fundamental counting principle. If we've got 2 outcomes, and then 3 outcomes, and then another 3 outcomes, what is 2 times 3 times 3? 18. So that means my sample space should have 18 possible outcomes. So I'm going to go ahead and number my paper down. 18. And then I'm going to write out my sample space. And like I said, I'm going to start with the very first activity, choose a second, and choose a third. So I could go milk, sandwich, veggies. Milk, sandwich, veggie. I'm going to put a check mark right next to that veggie to show that I've already written it down in my sample space. Then I'm going to do the same thing. I've got milk, sandwich, fruit. Milk, sandwich, fruit. Okay, I finished that one off. Milk, sandwich, chips. Milk, sandwich, chips. So I am now done with all 3 of these that are connected to the sandwich. I can go ahead and check that sandwich off. Does that mean I'm done with everything that does milk? No, because I still have milk and pasta. I still have milk and nuggets. So I could do milk, pasta, and veggies. I'm going to check that off. Milk, pasta, and fruit. Check that off. Milk, pasta, and chips. Check that off. Okay, I've done all the things that are connected to the pasta. I'm going to check that pasta off. But I still have the nuggets. Milk, nuggets, and veggies. Milk, nuggets, and fruit. And then milk, nuggets, and chips. Okay, I've now done the nuggets. So have I done everything that's connected to milk? Yes. What do I need to do next? The water. So this whole thing repeats again, but instead of milk, it's all the water. So we have water, sandwich, veggies, water, sandwich, fruit, water, sandwich, chips, water, pasta, veggies, water, pasta, fruit, water, pasta, chips, water, nuggets, veggies, water, nuggets, fruit, water, nuggets, and chips. All that has been checked off, and we filled in all 18 spots in our sample space. It's a nice, lovely, long map, and seeing the visualization of that map can help you to be able to answer questions. That if I wanted the probability that I was going to choose milk, not choose a pasta, but I could have fruit or chips. So I want milk. Okay, if I want milk, then that's going to be those first 9 choices right here. Those first 9 choices have milk in it. But I don't want pasta. I do not want pasta. So I cannot choose 4, 5, or 6. Sample space 4, 5, or 6, they have pasta in them. So that removes 3 choices right there. So now I'm down to 6 possibilities. And I would like fruit or chips. Fruit or chips, that means number 2, number 3, number 8, and number 9 are all possibilities. Okay? Item number 2 has milk, it does not have a pasta, and it has a fruit. Item number 3 is milk, not a pasta, but it has chips. Item number 8 has milk, not a pasta, and fruit. And item number 9 has milk, not a pasta, and chips. So we have 4 possibilities out of how many total again? Out of 18. So we could simplify 4 out of 18. That simplifies to 2 over 9, which comes out to 0.2 repeated, which is roughly about 22%. Being able to visually see what your sample space is helps you when you are trying to identify a very specific probability. Go ahead and take a moment to get that copied down, and then we'll move on to the next page. Let's go ahead and move on. So Brent, Hilda, and Saja are being placed in order of favorite students. Okay, place in order of favorite students. So we're going to make a diagram showing our possible orders. So again, if I'm placing them in order of favorite, once I choose one of them, can I choose them again? No, you cannot choose them again. Once I choose that person as my number 1 favorite, they can no longer be my second favorite or my third favorite because they've already filled the spot of number 1. So let's break this down. You have your first activity. Your first activity is to pick your first favorite student. So how many choices do I have for first favorite? 3. I have all 3 of them available for first favorite. I can choose Brent, I can choose Hilda, I could choose Seja. Okay, then I move down to my second activity. My second activity is to choose my second favorite student. So once I've chose Brent, can I choose him again? No. So I can only have 2 possibilities. I could choose Hilda or I could choose Seja. If I chose Hilda as my favorite, then I could choose Brent as my second or Seja as my second. And if I chose Seja as my favorite, I could choose Brent as my second or Hilda as my second. Now, once I've chosen my second favorite, I now need to pick my third. I need to put a placement for my third favorite student. So again, once I've chosen Brent and then I chose Hilda, then I only have Seja left. If I chose Brent and then I chose Seja, I only have Hilda left. If I chose Hilda and then Brent, I have Seja left. If I chose Hilda and then Seja, I have Brent for third. Seja's first, Brent is second, Hilda would be third. If Seja was first and Hilda was second, Brent would be third. So this is a mapping for a dependent situation. The first map was independent. The second map here that we're building, this map, is a dependent situation. Once you choose your first outcome, once your first outcome happens, you cannot have it again, so it's been removed from the situation. Okay, and like always, we want to go ahead and build our sample space. So this is the same kind of idea. For your first activity, you had 3 choices to choose from. You had 3 people you could choose from. For your second activity, second place, you only had 2 people that you could choose from. And for your third activity, you only had 1 person you could choose from. So what's 3 times 2 times 1? 6. So our sample space should have 6 possible scenarios, 6 possible outcomes. So we could go Brent, Hilda, Seja. Brent, Seja, Hilda. Hilda, Brent, Seja. Hilda, Seja, Brent. Seja, Brent, Hilda. Seja, Hilda, Brent. Those could be the orders of our sample space. Okay, I want you guys to do the exact same thing for this dependent event. I want you to tell me all the different ways that you can order the letters D-A-Y. The different orders that you could put the letters D-A-Y. Build a tree diagram, and I'm telling you right now it's dependent, so it's going to look similar to this. You're going to build your diagram and then write out your sample space. All right, let's take a look. For our first activity, how many choices do we have? 3, right? You could choose the letter D, you could choose the letter A, you could choose the letter Y. For my second activity, how many choices am I limited to? 2, right? If I chose D, then I would choose either A or Y. If I chose A, I'm left with either D or Y. If I choose Y, I'm left with either D or A. And then for my last one, I only have one outcome left to choose from. It could be D-A-Y, D-Y-A, A-D-Y, A-Y-D, Y-D-A, Y-A-D. So for my sample space, I've got 6 total ways that I could arrange these letters. D-A-Y, D-Y-A, A-D-Y, A-Y-D, Y-D-A, Y-A-D. You 3 in the back are about to get yourselves in big trouble. Number 5, we're going to make a tree diagram for the possible outcomes of flipping a coin and rolling a number cube. Flipping a coin and rolling the number cube. So we only have 2 activities. There are only 2 activities. Go ahead and build your tree diagram, and this is an independent activity, right? This is an independent compound event. Flipping the coin has no effect on the number cube. Rolling the number cube has no effect on the coin. Go ahead and build your tree diagram based off of that. Make your first activity the coin and the second activity the cube, which is a die. Okay, let's go over it. Flipping a coin, how many outcomes are there for flipping a coin? 2 outcomes, right? You can land on heads or you can land on tails. And then rolling the number cube, how many outcomes are there for the number cube? 6. So that means I'm going to have 6 branches going off here. 1, 2, 3, 4, 5, 6. I can land on a 1, a 2, a 3, a 4, a 5, or a 6. And same thing again. 1, 2, 3, 4, 5, 6. Okay. Whee. All right, so that's what the tree diagram is going to look like. Our sample space, very simple, has 12 outcomes because 2 times 6 is 12. So our first possible outcome, heads, 1. Second outcome, heads, 2. Third outcome, heads, 3. Fourth outcome, heads, 4. Fifth outcomes, heads, 5. Sixth outcomes, heads, 6. Then we've got 7th outcome is tails, 1. Then we've got tails, 2. Tails, 3. Tails, 4. Tails, 5. Tails, 6. Okay, so there's my sample space. Now, I could use my sample space to be able to identify the probability that I'm going to land on heads and a number that is less than or equal to 5. I could do that. Okay, that would be 1, 2, 3, 4, and 5 in my sample space, which would be 5 out of 12. Very, very simple. Or I could use what we learned with the with the fundamental counting principle. What's the probability that it's going to land on heads? What's the probability a coin lands on heads? 1/2, right? 1 out of 2. Okay? What's the probability that I'm going to roll the die and it's going to land on a number that is less than or equal to 5? Less than or equal to 5. 5 over 6. And then we could just multiply those. 1/2 times 5, 6 comes out to 5 out of 12. And look at that. 5 out of 12. Okay, so you could either use a map, or in some situations you could use the individual probabilities to be able to multiply them. Okay, on the next page, problems 7 and 8, I want you to work those out on your own. Problems 7 and 8 on the next page, work them out on your own. All right, let's take a look. For here, we want the probability that our coin is going to land on tails. What's the probability of tails, guys? 1/2. Probability that a coin is going to flip and land on tails is 1/2. Then we're going to look at the probability that we're going to roll a number cube or a die, and it's going to land on a value greater than 4. 2 over 6. 2 over 6, or 1/3 if you simplified it, but you don't have to simplify it yet. You simplify at the end if you need to. Okay, and then the probability for a consonant. Choosing a consonant on this 4-section spinner. How many consonants are there? 3 of them, right? B, C, and D. B, C, and D are my consonants. That's 3 out of 4. And then, like always, we will multiply those probabilities together, and it's going to come out to 1 over 8. Has a 1/8 chance of occurring, or 0.125, or 12.5%. Okay? I'll even write that part down. It's 0.125, which is equal to 12.5%. Always want to know how to convert back and forth. Okay? All right, number 8. Number 8, we've got some clothes in our closet. You've got 4 short-sleeved shirts and 2 long-sleeved shirts. So what I'm seeing here is a description of shirts. That's going to be my first activity that I'm focusing on. We've got 6 jeans and 2 pairs of leggings. That looks like it's going to be my second activity, which is my pants. Choice of pants. And then we've got 2 pairs of sneakers, 1 pair of flip-flops, and 3 pairs of heels. That sounds like choices for shoes. So we're going to set up our probabilities here. We want the probability that our first choice is going to be a long-sleeved shirt. So the probability for a long sleeve. How many long-sleeve shirts do we have? 2, right? We've got 2 long-sleeved shirts. There's 2 long-sleeve shirts out of how many total shirts? 6. So I have 6 total shirts. I have 2 that are long-sleeved out of 6 total. All right, probability that I'm going to choose jeans. How many pairs of jeans do I have? 6, right? I've got 6 pairs of jeans here. 6 pairs of jeans out of how many total pairs of pants? 8, right? 8 total pants. Okay, then we've got our shoes. We want the probability that we're going to choose flip-flops. How many pairs of flip-flops do we have? 1, right? We have 1 pair of flip-flops out of how many total pairs of shoes? 6, right? 1 pair that's flip-flops out of 6 pairs of shoes. And then we just multiply that. When we multiply that, we're going to get 1 out of 24. When we multiply that out, we're just going to get 1 out of 24. And then if we wanted to go ahead and do our conversion, we can divide 1 by 24. That's going to come out to approximately 0.04 0.416 repeated, which is approximately 4.16 repeated percent. What you're going to be doing today as our closing for the day, you've got 3 IXL skills that have been loaded into Google Classroom. Some of them are based off of fundamental counting principles. Some of it is based off of just finding the probability for compound events. There is not an IXL skill for tree diagrams that I can find yet. Go ahead and get onto Google Classroom and start.